Okay, in this video, I'm going to go through the 2024 paper, Demonstrate Understanding of How Physical Properties of Materials Inform Their Use. That's Achievement Standard 92029 for Level 1 Science in the NCEA curriculum. It's the paper, the exam that was at the end of the year as an exam. Okay, so in this paper, there are going to be 3 questions. Each question is going to be marked holistically. The whole question is going to be marked from a grade 1 up to a grade 8, maybe a 0 if you write nothing down. So with E7 and E8 being excellence, M6 and M5 and M6 being merit, a 3 and a 4 being achieved, and a 1 and a 2 being not achieved. And then we add all of those grades up to get a total, and then from that total you are awarded your overall mark for the exam. Anyway, each question is going to ask about, there's going to be a context given, and you're going to have to relate the properties of the material to how they're used. And how well you can write your explanation and link your ideas is going to determine the grade that you get. So let's just unpack the first question here. So here, first question is called Paper Electrical Circuits. So this is about a pencil containing graphite, that's carbon, has been used to draw an electrical circuit, which is an outline of a car. A 9-volt battery and a light emitting diode also part of the circuit. So in this question, and the picture isn't here because it's copyrighted, but basically you draw a car circuit and you have you use the graphite lines as the conducting wires to take the electricity from the battery to the LED. Now, if you've done preparation for this exam, you should have learnt about graphite, and you should have learnt about diamond as extended covalent substances. And in this case, they're going to use your ideas about graphite to explain these, or to answer these first 2 questions. Now, the first 2 questions are: describe 2 physical properties of graphite and link these properties to their use in the drawing and creating an operational electrical circuit. Okay, so in order for the electrical circuit to work, we need to be able to draw a graphite line on the paper that will conduct electricity. So the properties we need, we've got 5 choices here: melting point, solubility in water, electrical conductivity, malleability, and hardness. Okay, so melting point is not relevant here because we're not changing the temperature. I mean, it is relevant if you have very high voltage and your material might melt, but not in this case. Solubility, let's hope we're not going to put this paper in water. That's not going to be anything to do with it. But electrical conductivity, of course, is going to be used as whether it's a good conductor of electricity or not is going to be useful to determine whether it will make a good circuit. Here it says that we have 3 times 10 to the 5, which is 30,000. That would be 300,000 Siemens per meter, it's called, and that's the unit for electrical conductivity, and that is a good value for conductivity. It has a malleability that might be useful, but because we're drawing lines and we're not bending it, most probably not, but it's 4.8 gigapascals here. It's a brittle anyway. And hardness is 1 to 2 on Mohs hardness scale. Remember, Mohs hardness scale goes from 1 all the way up to 10 for diamond. And so here it's soft. So what are the 2 properties that are important for making a drawn electrical circuit on a piece of paper? The first one is, well, the hardness. It has to be soft. Graphite has to be soft so that when we rub the pencil against the paper, the layers will come off and stick to the paper. Okay, so we want when we rub the graphite against the paper, the graphite to rub off and not the paper to rub off. So here the property is soft. The pencil line is made of particles of graphite layers that have been transferred to the paper. So that's one of the properties. The second property, of course, if we want to make an electrical circuit, we need it to be able to conduct electricity. So that's the second property, and electrical conduction requires the movement of charged particles. So you should have learnt that if you need electricity to flow, you need charged particles. They are either going to be free moving electrons or ions. In this case, if we know graphite, and if we've learnt the properties of it, we know that graphite has free moving electrons, so it can allow the flow of electrons. So we've answered the first part of the question. So there are, in this question 1, there's a part A, B, and C. Part A is really just telling us which properties and why. Part B is giving a deeper explanation, and part C is going to be evaluation. Anyway, part B. Explain these two physical properties with reference to the structure and bonding of graphite. Okay, let's unpack the structure and bonding of graphite. So graphite is a two-dimensional honeycomb structure, right? So it's a 2D layered structure where each carbon is bonded to 3 other carbons by strong covalent bonds. There is 1 electron left on each carbon atom. That electron is called a delocalized electron, and that will be between the layers, because what happens with carbon is we make these hexagonal structured layers, so single layers like sheets of paper, but they are piled on top of each other to make like a big pile of, or a ream of paper, right? So graphite is like a ream of paper you might put into a printer. It has lots of different layers, and each layer, remember, contains these carbons that have these strong covalent bonds to 3 other carbons to make that honeycombed structure. Now, the other property, of course, is explain the two properties with reference to structure and bonding. Okay, so because the layers, so we've talked here, we've given the structure of it, and we've said, okay, it's got delocalized electrons. The next thing is the layers have weak attractions between them. So when we rub the bottom of the pencil against the surface of the paper, the layer is going to just rub off or come off, and we're going to make a line of these layers of graphite. So 2 things here is that the next thing is, so we've talked about the structure in the first bullet point. We've then said that there's weak attractions between them, which we'd already alluded to in the structure, but now we're saying also the graphite, because it has these delocalized electrons, they are free moving charged particles. They can conduct electricity along the pencil line. So what we've done here is we have taken the 2 physical properties and we've explained the properties with reference to the bonding and structure. So we've unpacked the bonding and structure and said they have this weak attraction force. They are soft because there are weak attraction force between the layers. They conduct electricity because they have these delocalized electrons that can move and conduct charge. Okay, so how do we, from this first part here, we can actually get, we can accumulate our opportunity to get a 1 through to a 6 in the mark for this question. So the N1 means, did we identify a physical property of graphite, or name it as a 2-dimensional covalent network? Yeah, well, that's well covered here. So we could have said, hey, one of its properties that's important is hardness, you get an N1. Or if you said, hey, it's a 2-dimensional network, you get an N1. N2, you need to put both of these things down. Identified a property and said that it's actually a covalent network, but it's a 2-dimensional one, not a 3-dimensional one like diamond, right? 2-dimensional covalent network. To get an A3, you need to describe the physical properties of graphite, name it as the covalent network, which we've already done for N2, and try to describe the structure of graphite and the strength of the attractive forces. So what we're saying here is you should have said, okay, we have these layers. Within these layers, there's strong covalent bonds between the carbon atoms. Okay, that's linking the attractive forces. Or we could have said between the layers, we have these weak attraction forces. So if you wanted to get an A4, you're describing the property of graphite, linking to the drawing of the electrical conduction. Names graphite as a 2-dimensional layer. Yep. Describes the structure of graphite and the relative strength of the attractive forces. Links to physical property usage to drawing and the operating circuit. Okay, so basically, if we want an A4, we are describing the structure of graphite and the relative strength of its attractive forces. So we're actually going to unpack both of the attractive forces to get the A4. To get an M6, we need to talk about what makes it suitable for the circuit. And we're really looking for these last 2 bullet points here. So it is suitable because it is soft and we can draw the circuit lines. That all links back, of course, to the structure of the graphite. And it is suitable because it can allow the conductivity of electricity. It can allow these free moving electrons to move along there. Now you get an M5 if some aspects of all of this we've put on this page is incorrect, right? So I guess the achieved points here are, look, you've described, so in the achieved points you would have described the physical property of hardness, described the physical property of conductivity, and described the structure of graphite. This is for A3 and A4, but for merit we need to, these last 2 bullet points is we're linking what those structures mean to the actual use of graphite to make this circuit. Okay, so what if we want an excellence? Well, the third question here is evaluate how graphite will behave when used to draw and create an operating circuit by linking 2 physical properties to the structure and bonding. So we're just really taking what we've already put and linking it specifically to the example. So first point I would put here again is I've put down the structure of the substance, right? So it's a 2D. It's carbon atoms held together by strong covalent bonds in 2-dimensional layers, and the 4th electrons are delocalized between the layers. Now here I haven't given all the detail because I gave it in the previous question. If I hadn't given the detail in the previous question, I would put it in this question. Now if I want to get a good grade for excellence, I'm going to reference some of the values they gave us. So it's good conductivity because it is 3 times 10 to the 5 Siemens per meter, right? As the electrons between the layers are free moving. So we have referenced the value that says it's a good conductor, and we've said that's because there are electrons between, and they can carry the electrical energy around the circuit that allows the LED to glow. Okay, so it has this high conductivity because the electrons are free and therefore can carry electrons around the circuit. So we've got 2 links in this sentence here. So the next one is the force between the layers are weak. That allows the layers to slide past each other, and that's why they have a value of 1 to 2 on Mohs scale, right? So again, we've done 2 links between 3 different points here, and I've given the specific value that was on the table. So I'm now going to relate what I've just said to the actual example. So the layers slide past each other onto the paper when it's rubbed against the paper. The weak attractive forces holding the layers together require a small amount of energy, you could say a small amount of force, to transfer the layer onto the paper. So we've talked about the forces of attractions earlier, but now I'm saying how does this relate to the paper? And then the last thing, when the pencil is rubbed against the paper, you can also say these layers from the pencil line, which is drawn on the outline of the car, the graphite layers of the line overlap each other, allowing the electrons to flow. So when you draw a line, it's like a conducting wire, but the reason it is because each piece of the graphite layer is overlapping and the electrons can move all the way along. And so that last point is, I guess, do you understand exactly? It's kind of like if you had a ream of paper and you just slid it all out to make a continuous line that you would walk on. That's what the graphite does when it makes this conducting line. Okay, to get an E7, you have to put this detail down, evaluate. Now evaluate, remember, is when we're writing these evaluations, we are linking multiple ideas together and we're making sure we're referencing to the data values that we were given. Why, and we also need to link it at the end to why it will make an effective circuit. If we're some evidence missing, we're E7. If we have all the evidence here, we're at an E8. So what's really important here to make sure that you get that excellence here is you've talked about the relative forces. You've talked about them being strong within the layers and weak between the layers. And that is how they give you in the grades from 1 to 8 in the first question of the paper. And it's going to repeat in the rest of the parts of the paper. Okay, so question 2, called electrical fire. Carbon dioxide fire extinguishers can be used safely to put out electrical fires. These extinguishers are filled with non-flammable carbon dioxide, CO2 gas. So here's a picture of a carbon dioxide extinguisher. It says the physical properties of carbon dioxide in the air. Physical property of CO2 density is 1.98. That's kilograms per cubic meter, 1 meter wide, 1 meter deep, and 1 meter high. Air, its density is 1.2, so it's less dense. Electrical conductivity, well, they're both insulators. Describe the physical properties, this is part A, of carbon dioxide and link these to the physical properties for the safe use of carbon dioxide to prevent oxygen air from fueling a fire. Okay, so what are the two properties? Well, they're obviously going to be the two properties they've given us. So the first one is carbon dioxide is denser than air. Now what that means is that carbon dioxide will sink to the ground, right, and it will displace any oxygen or air that's there, and it will put the fire out. The second thing about carbon dioxide, it is an insulator. So because it's an insulator, if you've got any electrical appliances there that are in the fire or causing the fire, the electricity will not be conducted through the carbon dioxide gas to somebody to give them an electric shock. That wouldn't necessarily be true if you had something like water, which might conduct electricity if you used it to put out a fire. Okay, so we've described two physical properties and linked them to its use. The next thing, explain these two physical properties with reference to structure and bonding of carbon dioxide. Okay, so this is a bit more complicated than it seems, but let's just start with explaining the structure and bonding of carbon dioxide. Carbon dioxide is a molecular substance. Consists of discrete molecules containing non-metal atoms held together by strong covalent bonds. But it only has weak attractions between the molecules. That means it's in the gas phase, right? So because it's in the gas phase, that's why it's not very dense. But it's not a good explanation. We haven't got a good reason to say why the carbon dioxide is more dense than air. You'd have to go into the molar mass of the molecules, how much of the atoms, how much each atom weighed, and that carbon dioxide has a carbon and 2 oxygens, where in air, oxygen just has 2 oxygens. That makes that particle heavier. But we actually don't have the knowledge to unpack that yet, so this is as good as we're going to get. But we can say, hey, because it's denser than air, it's going to drop to the ground, replace oxygenated. We just kind of repeating what we said in the previous question. Okay, one thing about carbon dioxide, it is a discrete molecule. It has no charge and it has no free electrons, so it's not able to conduct electricity. So that's really a very good explanation of a property. That is why linking its physical property to the structure, that's why it's an insulator, right? That's why carbon dioxide insulates. So N1, did we identify that carbon dioxide was a discrete molecule or molecular substance? N2 is, did we describe its structure? So we've said the type of substance. So here we've said, okay, it is a molecular substance and it's made up of particles held together by weak attractions. That would be okay. A3. If we want to get an A3, we have to actually talk about the structure of carbon dioxide, but link it to the strength of the attractions between the atoms in the molecule, or the strength between the molecules. Strong covalent bonds within the molecule, or weak attractions between the molecules. We also need to have an attempt to link why we would use it to put out a fire or electrical fire as an extinguisher. If we want an A4, we have to do the same. What's different here? Describes the structure relative of attractive forces between or within the molecules. and physical properties of carbon dioxide. So in A3, you just needed to link it to one of the physical properties, but in A4, you need to have talked about physical properties, right? So talked about the two properties, density and electrical conductivity. So they might give you an A3 if you just had one of the properties, but A4 you need both. To get an M6, the difference here for the merits is you need to give the relative strength of all of the forces. So you need to have really done this third paragraph here completely. You have to say there's very weak attraction between the molecules, but they're held together by strong covalent bonds, the atoms within the molecules. Okay, and link that to its use to put out a fire. And M5 is going to be, we missed a wee bit of this explanation here. Maybe we didn't write discrete molecules. Maybe we weren't as clear as we could have been. They'll give you an M5. So that's how we get an N1 to M6. Then we've got question C, and question C we're going to use to get our E. So question C, evaluate. This is going to be to get our excellence answer here. How carbon dioxide will behave when used as a fire extinguisher, linking the two physical properties to the structure and bonding. Okay, so carbon dioxide consists of discrete molecules we talked about, of non-metal atoms held together by strong covalent bonds. Now, of course, we recognize discrete molecular substances, right? We recognize molecular substances because they are commonly or they are made from two non-metals bonded together, right? Well, from the formula. So putting the non-metal in there is quite good. But weak attractions between the molecules. This allows the molecules to move freely. And that's important because that's what allows this to be a gas. Also, we can see here that these discrete molecules are heavier than the air particles. They must be for the carbon dioxide to be more dense than the air particles. And actually they are. The molar mass of a carbon dioxide is, I think, 44, where the molar mass of oxygen gas is 32, and the molar mass of nitrogen gas is 28. So it is heavier than the other two gases that commonly make up here. Carbon dioxide is more dense in air. We, again, remember from the last one, we need to give the data, chuck that in there. So we're putting down the density values, 1.98 compared to 1.2. So it sinks to the ground and covers the flames to prevent the oxygen. It actually covers the fuel being whatever is burning. The flames are what we see above the fuel, but the flames is fine here, to extinguish the flames of the electrical fire. As shown in the table, carbon dioxide is an insulator, so that sentence there is a reference to the table. And remember, you're not going to get an excellence without putting the reference to the data. The discrete molecules of carbon dioxide do not have any free moving charged particles. That is, they have no electrons and they aren't an ion, so they will not conduct electricity. It will stop the electrical current from flowing to people nearby. Well, it won't allow, not necessarily stop isn't the best word, but it won't allow electrical current to be conducted through it. So yes, in that way it will stop it. And because they're free moving, they can surround the source of electrical fire, preventing the charge to flow through the air. Carbon dioxide is a safe way of extinguishing the fire. Okay, that's just a concluding sentence there. Anyway, so in E7, did you evaluate the structure? Yes. Now, we didn't put all the details of the structure here, but we did in the previous question. Do we give relative strength of attractive forces? Yes. Physical properties of carbon dioxide made suitable? Yes, and we linked it. But if there's some linking evidence missing, we're at E7. Okay, if part of this is missing, maybe we didn't reference for one of these points here. Maybe we didn't say as shown on the table. They might give us an E7. E8, we're going to do everything here. Okay, let's have a look at the last question. Okay, question 3. Harakeke is New Zealand flax. Long upright leaves that can grow up to 4 meters in length, where the green flesh is removed by scraping a long white fiber, a polymer it's called. Okay, so we're going to be referencing polymers here, called muka, is revealed. This fiber can be spun or plaited. Muka fiber is a natural polymer material. Okay, the spun muka can be used for many things, including making a kupinga, a fishing net. A kupinga could then be weighed down with stones that would help the net sink. Okay, so what we're talking about here is the flax. Okay, this is the green flax. If we scrape the material off it, we're left with this muka, which is these long fiber filaments here, and they're actually made up of polymer chains, a special type of cellulose polymer actually. And then if we take this can be wound or woven into a fiber that we can then tie into a net. And here's our net, or our kupinga. Okay, so that's our net. So they've given us a table here about 4 different substances, materials that we might make a net out of. Muka, hemp, wool, and glass. And they've given us a value for Young's modulus, which is the smaller the value, the in gigapascals, the more malleable the substance is. And you can see here that wool is the most malleable, muka is more malleable than hemp, but glass is not very malleable at all. So describe 2 properties of muka that would link these 2 physical properties to the use of making a working net. Okay, so here's the other property, it's insoluble. Now, if you know anything about fishing nets, you put them in water. So if they were soluble and we put them in water, they would disintegrate and they would fall apart, and you wouldn't be able to catch any fish. So of course that's going to be an important property. It's a kind of common sense property. And then malleability is, if you know anything about a net, we need, when a fish goes into a net or is caught, it needs to be able to move and bend without breaking. We also need to be able to move and bend the fibers and knot them together in order to make the net. So the 2 properties are malleability, the fibers need to be able to bend without breaking for the net to be made and used. That makes sense. And it needs to be soluble, as we don't want the net to dissolve when we're trying to catch fish in water, because we place nets in water. Now, muka fiber is a polymer, a long chained molecule made from repeating units with strong covalent bonds between atoms within the chain, but weaker attraction between the chains. So we're thinking of like a bowl of spaghetti, right? Each spaghetti length has strong attractions within it, but between the pieces of spaghetti are weak attractions, but enough to kind of hold it together as a mass. So explain these 2 properties with reference to the structure and bonding of muka, which is the polymer, right? What is the fiber created by the polymer? So muka fibers can be spun and knotted to make a net. These can happen because the forces of attraction between the polymer chains are weak. Remember, we're thinking about the spaghetti analogy. The attractions between the lengths of spaghetti are weak, so therefore we can change the shape. The weak forces of attraction can be broken with little energy. So we're putting the idea, like we did earlier in the first question, about a little bit of energy is needed to break these weak attractions and reform the fibers once they've been worked. Now, when we're talking about reforming here, what we're really talking about is we can bend them and we can knot them. The polymer chain can be easily moved relative to each other, so the net can easily change shape. So when a fish goes in there and we pick it up, it can change its shape and it won't shatter. It's not brittle. So to be used as a net, muka fiber needs to be insoluble in water. The forces of attraction between the polymer and the water molecules must be very weak, so they don't overcome the strong attractions between the polymer chains. Or actually, they're weaker attractions. The strong covalent bonds within the chains and the weak intermolecular forces holding the chains together. Now remember, we've got weak attractions between the long lengths of spaghetti. We don't want those to dissolve, and therefore those attractions have to be stronger than the attractions the muka polymer has to the water. This allows the net to stay whole when catching fish. Okay, that's a nice clear explanation, those 2. So N1, if we can identify a physical property of muka, or that it is made up of a polymer with repeating units or strong covalent bonds within the chain and weak forces between them, we get an N1. And N2 is an and here, so a property, and it's made up of a polymer repeating units in a chain. A3, we're doing what we put in N2, but now we're going to link it to its use as a net. Okay, so we have to say it is insoluble, so it's good to use a net because it won't dissolve in water, or it is malleable, so it's good to use as a net because it can change shape when we get fish in it. A4, as above, but actually gives good links to the net. So for A3, it attempts to link it to the net. It isn't super clear or it isn't perfect, but for A4, you're going to make both attempts to link to the net. M6, it explains the structure. Now, when we're explaining the structure, we're talking about the relative strength of attractive forces. Now, what we mean by relative strength is that the atoms are strongly held together in the chain, and the polymer chain, or the repeating units are strongly held together in the polymer chain, but the polymer chains are weakly held to each other. Okay, you can also talk about the forces between the polymer chains and the water are not as strong as the forces that between polymer chains and polymer changes. Okay, if this is aspects of this are incomplete, you get an M5, and that's how we get a 1 to an M6. Okay, let's look at the excellence part of this. Okay, so evaluate how muka will behave when used as a kupinga, a net, by linking the two physical properties. So we're again just going to coalesce all this information together and write a couple of paragraphs. The first paragraph here, it looks kind of big, but okay, to be used as a kupinga or a net, the fiber needs to be able to be plaited and woven and then knotted together. Okay, so we actually need to make a fiber out of it, and we need to knot it to make a net. To be plaited or woven, the fibers need to be able to slide past each other easily and malleable. So we're saying, okay, to be able to do this, it has to be malleable. And then we are going to remember the link to the actual value that was given in the table. So it has a Young modulus of 8.6, meaning it is not brittle and hence it is malleable. So the long chains, and now we're going to relate it to a structure. The long chains of repeating units have strong covalent bonds, but weaker attractions between the chains. The weaker attractions between the chains allow the fibers to slide past each other, and that's why they're malleable. So we're linking, we have to say it's malleable because we're told in the table, here's the value, but there is a property of the actual particles that make it malleable, and we need to give that, and we need to link all of that together to the net as to why it needs to be malleable, right? So we're told it's malleable here. It is malleable because of these attractive forces between the particles, and because it's malleable, I can use it for this particular context as a net. And then we do the same thing with its solubility. So we need to say, okay, it has to be insoluble, this net. So the table tells us it's insoluble. We need to put that down. If you don't, if you miss it on this one, you got it in the previous one, that's an E7. If you don't put it down on either, then that's back to a merit. The forces of attraction between the polymer and the water molecules are too weak to overcome the attractions between intermolecular forces holding the fibers together, right? Because even if, I mean, they're not as strong as the attractions within the fibers, but if they were as strong as the attractions, stronger than the attractions between the fibers, the pieces of spaghetti, then it would just all pull apart, right? They would all fall apart, and when we put it into the water, but it doesn't, so that's good. And we need to link it to, it needs to be able to be placed in water. That's the reason, right? It needs to be insoluble because we're going to place it in water. So that's really important to say. That's where the fish are. The net has to go in there. So we can get an E7. If you had some data missing. With the E8 here, you actually need to justify its suitability as a kupinga or a net, right? So you need to say, hey, it will be suitable as a net because it's insoluble. And we know it's insoluble because we know that these chains don't have as a strong attraction to the water as they have to each other. And we know it's insoluble because they told us in the table. And you use that same argument to say why it's malleable. So you've got those sort of multiple ideas. We're talking about, we're given data, but we're explaining the particles and we're linking it to what it's used for. That's what gives us the excellence. I hope this video has been useful. I know that there isn't a lot of good information about how to answer these level 1 science papers, but all the best with your exam at the end of the year.